All right, here is our exam 3 review. Keep in mind these questions will vary since they're multiple choice, so be sure you know each topic well. The first question, give the set of 4 quantum numbers that represent the last electron added using the Afbal principle to the zinc atom. Let's take a look at zinc atom. If you look at zinc atom, it's zinc right here on the periodic table where you have 1, 2, 3, 4, fourth period. So the configuration would be argon, 4s2, 3d, 10. So at the end of this part here, that's d10 because this whole region is d1 through 10. So over here, that means for zinc, the configuration is going to be whatever argon is plus 4s2 and 3d10. Hence, the last electron in there is going to be the 10th electron in 3d. So that means if we have level 3d, so it's -2, -1, 0, +1, +2. So this is our ML levels. Okay. And it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the last electron is this guy, the one I circled. The last electron is spin down. So we know that ML is +2 and it's spin down. So MS is -half. And then the fact that it's level 3, M is 3. When it's d orbital, L is 2. So you should look for a combination with N is 3, L is 2, ML is +2, and MS is -half. That means one of your answer choices fits. It's N3L2, ML2, MS -half. All right, diamagnetic species. It says choose the diamagnetic species from below, and you have choices of I, Ni, Pb2 plus, N, or none of the above. So diamagnetic means you have to have all paired electrons. So let's take a look at each one of these. Paramagnetic means you have at least one unpaired. So the first one is I. Took a look at I right there. Okay. So I is level 1, 2, 3, 4, 5. So you'll have 5p5 as the last one. Okay, so it's everybody in there and then 5p5. So the last level, all the rest are filled before that, and then you hit 5p5. And then when you draw level 5p, it's not fully filled at 6 because it only has 5. This one is paramagnetic. So iodine is paramagnetic. Let's look at nickel. Nickel is right here. Group 1, 2, 3, 4, 5, 6, 7, 8. The 8th one in your transition metal. So you'll have 3d8. Is it 8? 1, 2, 3, 4, 5, 6, 7, 8. Yep. So if you have 3, 8, you'll have, when we draw 3D out, although 8 looks like it's even numbers, we'll see that it's actually still unpaired. 1, 2, 3, 4, 5, 6, 7, 8. You still have 2 unpaired, so nickel is also paramagnetic. So let's take a look at Pb2 plus. Pb2 plus, Pb is right over here on below on group 4. It has everything in xenon plus a bunch of electrons, and then you have in level 1, 2, 3, 4, 5, 6, 6p. There's 2 electrons that will be lost because if we're trying to get Pb2 plus. So I'll go ahead and write down the atom form, and then we'll lose the p electrons for the ionic. So Pb is xenon, and we have level 6s that's filled. And then we also have 4F14 that's filled. But then we also have 5D10 that's filled. So I'll go ahead and write that down. And then you have 6p2. So we're going to lose these 2 electrons. Okay, so that means what you'll have is when you lose these 2 and you get Pb2 plus, you'll have everybody that's filled. S is filled, D is filled, F is also filled. Because for F14 means 1, 2, 3, 6, 7, 8. See, every single one is filled. So this one here is diamagnetic. The Pb2 plus is diamagnetic. What about nitrogen? Let's take a look at nitrogen. It is 1s2, 2s2, 2p3. So the last one is 2p3. And you'll see it's half filled, so it's paramagnetic as well. Okay, let's go to the next question. Ground state electron configuration for chromium 3+. So let's take a look at what chromium looks like without the ion. It's 1, 2, 3, 4. The fourth one on level 3D. So it will be everybody in argon. And then 4s2, 3D, 4. And then you want to lose the 3. Since there's no way we can make 3D 5, so we're just going to take them out from the level 3D. So we take 3 out here. What you have is AR 4s2, 3D 1. Now, let's take a look at the next question. Identify the species that has the smallest radius. If you have all of them the same element, just remember the more electrons it has, the more negative charge, the bigger it will be. The smaller number of electrons, it will be the smaller. So that means if you become positive charge, it becomes smaller. The more positive it is, the smaller. So that means out of As2 minus, As3 plus, As plus, As4 plus, and As3 plus is the most positive one. This would be the smallest, and the biggest one would be As4 negative. All right, let's go to the next question. So this question asks us, what period 3 element? So we're in period 3 element. It says has the following ionization energies, where you see all of them are in values of kilojoules per moles. The first level is 1,000. The second level is 2,250. Third level is 3,360. Fourth level is 4,560. Fifth level is 7,010. Sixth level is 8,500. And then seventh level, it skips a huge amount to 27,100. So that means this is in period 3, but the discrepancy between the 6 and 7 here tells me group 6 is on the outside. Once it's in the 7th electron here, it becomes on the inside level. So up to 6 is the valence. So that means if there are 6 valence, this is in group 6, and it says it's in period 3. So if you look on period 3, 1, 2, 3, group 6 would be sulfur. So if you look at different patterns here, if the pattern of a big jump happens earlier, like say maybe on the 5th one, the 5th one is a big jump, then you'll say, well, that means it had 4 valence electrons. Because it happened on the 7th one, I know it had 6 valence electrons. All right, let's take a look at the next question. It says, list the following compounds in decreasing electronegativity difference. So I have 3 compounds here, Br2, so we'll write down Br, Br. And then we have HBr, the next compound, and then we have Kf. So there's 3 different compounds here, decreasing electronegativity difference. This one, Kf, is an ionic compound. So it's very, very big difference in electronegativity. HBr is going to be a polar bond and a polar molecule. So the electronegativity difference is slightly smaller than ionic. Br is nonpolar. So that means this is the smallest one. In fact, it has 0 electronegativity difference because the atoms are the same. So that means the biggest one is Kf, the second one is HBr, and then it goes down to BrBr. So number 7, identify the compounds that has polar bonds but a dipole moment of 0. So the molecule is nonpolar, but the bonds are polar. So let's take a look at our options here. H2, CF4, KBr, AU, and AR. AU and AR are not even bonded. It's just a single atom. So we eliminate them right away. They're just atoms. So there's no bonds there. KBr is an ionic compound. How do I know that? That's because one is metal, one is non-metal. So if it's ionic, it's not going to have polar bonds because polar bonds belongs to something that has covalent bonds in a molecular compound. So the first two, H2 and CF4, have covalent bonds. H2 is H bonded to H in a single bond. CF4, if you remember, it looks like CH4 where you have a tetrahedral formation. The only difference CF4 and CH4 is F has the valence electrons. Okay, HH is nonpolar because the atom is the same. So the first answer is also eliminated. That leaves you only CF4. And let's explain why CF4 has polar bonds but dipole moment is 0. Because it's in tetrahedral form, each of these CF bonds are polar, but they cancel each other out because it's symmetrical. Therefore, CF4 is a molecule that is nonpolar with polar bonds. The next question asked is, which of the following elements can form compounds with an expanded octet? So the rule is, it's going to be the guys on the non-metal side, and it's below period 3 and below. So the first and second period, you can't do it. So F can't do it because it's on the second period. Aluminum is a metal, so we eliminate that. Metals don't do that. Sodium is also a metal, so we eliminate that. Bromine is possible. In fact, we see a lot of examples where we draw bromine with expanded octet. All right, let's go to the next question. It wants us to draw the best Lewis structure for XeI2. So for xenon and 2 iodines. So xenon, if you remember, we'll look on a periodic table. It's in group 8, so 8 valence. I is in group 7, 7 valence. So 8 plus 2 times 7, we get a total of 22 electrons. So we try to draw it out. So we put iodine on the sides because it's more electronegative. We start with single bonds and we fill it up. Now, if you remember, when you have 3 atoms and you fill it with single bonds, for everybody to have an octet, you would end up actually having 20 electrons. And I know I need 22, so I know this is going to have an expanded octet, where xenon is going to have 3 lone pairs and 2 bonded pairs, 5 groups. So the best Lewis dot structure is an expanded octet here, and it would fit one of these options here. Says the next question, using Lewis dot structures and formal charges, which of the following ions is most stable? OCN negative, ONC negative, or NOC negative? So the first thing you want to think of is I always put the more electronegative atoms on the outside. So anything that has oxygen, out of O, C, and N, C is the least electronegative, so it should stay in the middle. O and N should go on the outside. So I will say these guys are automatically eliminated, and the best one is going to be OCN. I want to go further and show you the formal charges. So you don't have to like calculate it unless they ask for it, but this is a good way for us to make sure we understand why this one is good, why we put the electronegative ones on the outside. So when you draw OCN, you have OC triple bond N, and you count the valence electrons, you'll see that this matches. Okay, we keep the electronegative on the outside. Now remember, to get the formal charges, we count the valence minus the half of the bonded electrons, not pairs, individual electrons, and minus the lone electrons. So I have oxygen, which is group 6. Oxygen is group 6, so I have 6 valence electron. Carbon is 4 valence. Nitrogen is 5 valence. Now, how many bonded? I have 2 bonded, so half of that is just 1. And then lone pairs, lone electrons, 1, 2, 3, 4, 5, 6. Half of that, not half of that, 6. We half of the bonded. So 6 minus 1 minus 6, you end up getting -1. This is good because we want to put the negative values on the most electronegative atom in the structure. Carbon is 4 valence minus half of bonded, which is 4 because 8 is all the bonded, and we have no lone pairs, no lone electrons, so this is 0. 4 minus 0 equals to 0. And then for nitrogen here, I have 5 valence, and I have 6 of them that are bonded, so half of them is 3, and then 2 electrons, so 5 minus 3 minus 2, also 0. This formal charge configuration is the best possible option. And that's why OCN negative is the most stable structure. All right, go to the next question. Using the bond energies provided use the bond energies below right here to estimate delta H reaction, standard delta H of reaction in kilojoules for the reaction below. The reaction is C2H4 gas plus H2 gas equals to C2H6 gas. The question mark is for the delta H naught reaction. And it says, report your numerical answer with what decimal place without units. Do not use scientific notation. Our bond energies are listed in kilojoules per mole, where C single bond to another C is 339.3 kilojoules per mole. C single bond to H is 415.2 kilojoules per mole. C double bond to C is 605 kilojoules per mole. C triple bond to C is 836.6 kilojoules per mole. H single bond to H is 427.6 kilojoules per mole. So these are the energies per bond, and you have to remember when you break bonds, it's a positive value, and when you form bonds, it's a negative value, and you add them all up together to get the delta H of the reaction. So to do this, you need to recognize that C2H4 is going to be drawn as a double bond C. So you have to draw the Lewis dot structure out so you know what type of bonds you're breaking and what type of bonds you're forming. Once you have C2H6, you'll see that this one changes configuration to an sp3 because now you have 6 hydrogens that you got to put around, and this is an sp2 carbon for the reactants. So over here, we're going to have to break this bond, C double bond C. So break 1 C double bond C. We also have to break the hydrogen, 1 H single bond to H. And we will have to form the C to the, we have to form the C and a C to be a single bond. And then we have to form 2 of them. So let's say if we have the 2 on the top like that, we'll form CC bond, we'll form 2 CH bonds, 2 C single H, single bond H. Okay, so when we break, this is a positive value. C double bond C is positive 605. H single bond H is positive 427.6. And then when we form single bond CC is negative 339.3. And then you have 2 of negative 415.2 from forming 2 C single bonded to H bonds. Let's add them all up together. So delta H naught reaction is going to be positive 605 plus 427.6 minus 339.3 minus 2 times 4, 15.2. So I can either say plus and then plus negative, I just put the minus in it. Okay, same thing. So when you add them all together, we want one decimal place. That means we'll keep 137.1. And you don't need to type the unit, but the unit is going to be kilojoules. All right, the next question. When you have CO3 2 negative, the question asks you, what is the oxygen to oxygen bond angle in CO3 2 negative? So we got to count how many valence electrons, draw it out, and then we can tell what type of geometry it is to tell the bond angle. So carbon, oxygen, 3 of them, 2 negative. 4 is the group of carbon, so 4 valence plus 3 times 6, because oxygen is in group 6, plus 2 electrons from there. So you have a total of 24 electrons. Now, if you remember, we did draw CO3 2 negative in our examples from class. And you'll have to remember, this is one of those that has a resonance, but you can't decide where you put the double bond, because if you didn't do a double bond, you would end up with 26 electrons, and that's wrong. We need only 24, so we have to put one double bond in, and we'll have to draw a resonance for each kind. But since we don't really have to worry about resonance drawing, we just want to know what structure, geometry it is. You can tell here that this is going to be 3 groups on the carbon, and there's no lone pair, so this is going to be a trigonoplanar geometry where the bond angle is 120 degrees. All right, let's look at the next question. We're going to look at the structure of aspirin. In this structure of aspirin, you have to remember to fill in the lone pairs of electrons according to the octet rule to determine the correct number of electron groups around those atoms that are labeled. The Lewis dot structure does not show actual geometry of the molecule. So it just shows you the Lewis dot structure here, and it doesn't even fill in the lone pair, so you need to know where the lone pair should go. On A here, you'll see there's 2 bonds, but if you need an octet, you need 2 lone pairs on it. Okay, on B, the carbon, it has 1, 2, 3, 4. So that one already has an octet, so you're good. I'm going to go ahead and fill in the lone pairs with the oxygen wherever I see that it's needed. It's just good habit. Okay, so on A here, because we know it should have 4 groups, 2 bonded and 2 lone, this geometry is going to be sp3. The carbon is single bonded to an O and single bonded to something else and double bonded. So there's 3 bonds and no lone pairs. This is going to be sp2. So the answer should be sp3, sp2. Now the next question asks us, list the number of sigma bonds and pi bonds in a triple bond. A single bond is 1 sigma bond. A double bond is 1 sigma, 1 pi. A triple bond is 1 sigma and 2 pi's. Next question, we have a molecule where we have carbon, 2 carbons, and then nitrogen bonded with some hydrogens and oxygen and chlorine. But we're focused on the carbon that's labeled 1, carbon that's labeled 2, nitrogens that's labeled 3. And it asks you determine the molecular geometry of each of the 3 labeled atoms. We can even go further and tell you the bond angles and the hybridization as well. So in this case here, the first carbon has 4 bonds, no lone pair. So this would be sp3 hybridization, and it would be tetrahedral. And the bond angle is 109.5. The second carbon is also tetrahedral with 4 groups. Same exact thing as the first carbon. The third atom is a nitrogen. It has 4 groups, but one of them is a lone pair. So that means this one is sp3 hybridization still, but it's trigonal pyramidal. You can kind of see the pyramid on the bottom there, and then the lone pair is on the top. And the bond angle is slightly less than 109.5. With one lone pair, we typically say it's around 107-ish. So the geometries here for each one will be tetrahedral, tetrahedral, and trigonal pyramidal. Oops, actually, no, this is not 4 groups. This is only 3 groups. Because it's double bond is considered as one group here. Okay, let me fix that. sp2, trigonal, planar. And this is 120 degrees. So it's actually trigonal planar. And then we have tetrahedral. And then we have another sp3, but trigonal pyramidal, 109.5, a little smaller. So let's see. It would be, all right, the highest viscosity would mean we would need the highest intermolecular force. So it says choose a substance with the highest viscosity. It's really asking which one has the highest intermolecular force. So we have our option of CBr4. CBr4 is like CF4 or CH4. It's going to be nonpolar because it cancels out. So this is only this is London dispersion. So it's like the weakest one, right? CH14 is also London dispersion, a little bigger. Because CH bonds are all nonpolar. And then you have CH3, CH2, and then double of that, and then you have CO. So when you have the CO here, this makes it polar. So that means this has dipole-dipole. And then you have the OH and the OH. This tells us we have hydrogen bonding. So hydrogen bonding is stronger than dipole-dipole. So right now, D is the strongest. Let's take a look. C2H4Cl2. So the fact that we have C2H4Cl2 on these guys are all stuck to the carbons. So that means it's going to be somewhat polar because we have CCl depending on where it's bonded. So this one also has dipole-dipole. But it's not hydrogen bonded. So hydrogen bonding is the one that's going to be the strongest and the most viscous. All right, let's go to the next question here. The next question talks about ethanol. Ethanol, that is C2H5OH, it melts. So this is the melting point of negative 116.69 Celsius. Molar mass of ethanol is 46.08 grams per mole. The enthalpy of fusion, delta H fusion, is 5.02 kilojoules per moles. The specific heat of the solid and the liquid ethanol are, this one is a solid, 0.853 joules per grams Kelvin, and for the liquid, 2.222 joules per Kelvin, joules per grams Kelvin. How much heat in kilojoules is needed to convert 23.06 grams of solid ethanol at negative 136.82 Celsius to liquid ethanol at negative 59.05 Celsius? Please report your answer with 2 decimal places without units. Don't use scientific notation. So they told you it's solid, and then it's going to melt, and then they want you to raise the temperature to liquid at that temperature. So I know there's 3 temperatures involved here. I'm just going to go ahead and draw a graph. It's not to scale, but at least it helps you figure out how many steps we have. The lowest temperature is negative 136.82. And then it's going to go up until hit the melting point at negative 116.69. And then we're going to raise the temperature once it's liquid to negative 59.05 Celsius. So it's going to go up, hit the melting point, melt, and then go up again. And we stop right there because that's what the question asks. So we have 3 steps. 1, 2, 3. Step 1 is a solid. Step 2 is solid turning to liquid. Step 3 is a liquid. So therefore, Q1 is going to be MCS of the solid, delta T. Step 2 is Q2 is number of moles N times delta H of fusion, which is given to us. And then step 3 is Q3 would be MCS of liquid, delta T. So the M is the mass, so 23.06 grams. And then the solids number is 0.853 joules per grams Kelvin. And the reason how you know it's grams here because we have grams and grams cancel out. Now remember when we do delta T, Kelvin and Celsius is going to be exactly the same. So I'm not going to worry about changing the units. I'll just write the same number down, knowing that if I convert a unit and subtract, I still get the same delta T in Kelvin or in Celsius. So I'm going to put down negative 116.69 because this is the final, and then minus the initial, which becomes positive 136.82. So this is T final minus T initial. And that's going to be in Kelvin. So that would cancel the grams in Kelvin, so you get an answer in joules. If we want to answer in kilojoules, we have to divide by 1,000. So over here, you get 395.96, and you divide that by 1,000, 0.39596. I'm writing extra numbers down, but you only need like 3 clicks here. I'm just going to write a bunch of numbers down, and then at the end, we round to 2 decimal places. All right, for step 2, we need number of moles. They gave us the molar mass of ethanol, so we would have to take 23.06 grams divided by 46.08 to get the moles. So I'm going to go ahead and do that part here. 23.06 grams. The conversion. It's 46.08 grams. And then times delta H fusion, which is 5.02 kilojoules per mole. So the answer is in kilojoules. And you get, I'm going to write down all the numbers, bunch of numbers again, but it's really just 2.51. Keep writing. 2, 1, 7, 8. All right, step 3. Q3 is MCS now for liquid delta T. So we go 23.06 grams. The CS for liquid is 2.222 joules per grams Kelvin. So the grams will cancel out, and the temperature, remember, Celsius and Kelvin, delta T is the same number. So negative, final is negative 59.05. And then minus a negative number will be positive 116.69. So that's going to give me 2950.776 joules divided by 1,000, 2.950776 kilojoules. I'm going to add them up and only keep 2 decimal places. And that should give me 5.86 in units of kilojoules. All right, let's go to the next question. Define critical point. Critical point is where above that temperature and pressure, you get supercritical fluid. This definition where the temperature and pressure with liquid, solid, and gas are equally stable in equilibrium, this is called triple point. The other ones are just made up stuff. Which of the following is considered a non-bonding atomic solid? So this is going to be ones that are in noble gas group. So noble gas is neon. If you take a look, that's our option here. These are metal, 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 and this is a molecular compound. All right, it says electron geometry, molecular geometry, and polarity of SO2. So let's draw SO2, group 6 and group 6. Sulfur and oxygen are both in group 6. So I have 18 electrons total, and I'm going to draw SO2. And SO2, you end up with O and O, and then you'll have to have double bond on one side, and then lone pair. So this should give us 18 because it's 8 and 8, that's 16, and then 2 more. If you didn't have a double bond, you would need 20 electrons, and that's why we put a double bond in here to make sure it fit 18. So in this case, we have one lone pair, so the bond angle is less than 120 degrees. The electron geometry should be trigonal planar, and the molecular geometry is going to be bent because when you cover this one, it's bent. And overall, because it's not symmetrical, the oxygen side here is going to be more negative than the sulfur side because they're both pulling down. So this molecule is polar. So e.g. electron geometry trigonal planar, and then it's bent and it's polar. So that's all we have for the review, but keep in mind that these are just general topics and the questions that you get will vary. So be sure to practice it multiple times and be comfortable with the topics.